Hey everyone. Today, I want to talk about properties of the conjugate of a complex number, as well as the triangle inequalities. So first, let's recall that the conjugate of a complex number z equals x plus iy is x minus iy, where the conjugate is denoted by putting an overbar over the complex number. So essentially all the conjugate is simply the complex number, except you flip the sign of the imaginary part. Okay, now let's go ahead and go over some of the properties of the complex conjugate. So for any z1, or z2 in the complex numbers, we have a bunch of different properties that hold. Property A says that the conjugate of z1 plus or minus z2 equals the conjugate of z1 plus or minus the conjugate of z2. So essentially, the conjugate of a sum or difference equals the sum or difference of conjugates. Property B essentially says the same thing, but for multiplication. So we have that the conjugate of z1 times z2 equals the conjugate of z1 times the conjugate of z2. Property C says the same thing for division. So the conjugate of z1 over z2 is equal to the conjugate of z1 over the conjugate of z2. Property D states that the conjugate of z equals z. So taking the conjugate twice simply returns the original number. Property E says that the modulus of the conjugate of z equals the modulus of z. Part F says that the modulus of z squared equals z times the conjugate of z. Property G says that the real part of z can be expressed as 1/2 times z plus the conjugate of z. Property H states that the imaginary part of z can be expressed as 1 over 2y times z minus the conjugate of z. And finally, property I states that the conjugate of e to the I phi is simply equal to e to the negative I phi. And recall from my previous video that e to the I phi is the polar form of a complex number. And I encourage you to actually try proving some of these properties because they make for really good exercises and they're not too difficult. Okay, before we move on to the triangle inequality, I want to actually show that there's a really interesting way that we can rewrite the inverse of z by using property f. So note that z inverse is equal to 1 over z, and if we multiply the numerator and the denominator by the conjugate of z, we get the conjugate of z over z times the conjugate of z. And by property f, z times the conjugate of z is equal to the modulus of z squared. So we can rewrite this as the conjugate of z over the modulus of z squared. So this is another way that you can represent the inverse of a complex number. And it may come in handy when you're trying to do proofs or maybe cancel something out in some computation. Okay, now let's go ahead and go over the triangle inequality. So for any z1, z2 in the complex numbers, we have that the modulus of z1 plus z2 must be less than or equal to the modulus of z1 plus the modulus of z2. So what exactly is the triangle inequality getting at here? Well, essentially what it's saying is that the sum of two side lengths of a triangle in the complex plane must be greater than or equal to the side length of the third side of the triangle. And so let's go ahead and draw this out geometrically to understand it a little bit better. So let's draw in our imaginary and our real axis here. Okay, so we'll label this real and this one imaginary. Great. And let's say that we have a complex number z1 somewhere over here and a complex number z2 over here. And remember, geometrically, we can sort of represent complex numbers as like vectors in R2. So we'll draw these as vectors. Great. Now, let's go ahead and try to represent z1 plus z2. So remember, we're going to start from the origin, go out to the end of z1 here, and we're simply going to tack on z2. Great. Now, z1 plus z2 is the vector originating from the origin and ending at the tip of z2. So this is z1 plus z2, and this is z2. Now, what the triangle inequality is saying is that the length of this vector z1 plus z2 here, which is the hypotenuse of this triangle in this case, must be less than or equal to the length of the z1 vector plus the length of the z2 vector. So this is what the triangle inequality is getting at here. Okay, now let's go ahead and actually prove the triangle inequality. So what I want to start out with is the modulus of z1 plus z2 squared. And the reason why it's squared is because it's actually going to allow us to use property f that we just learned, which says that the modulus of a complex number, in this case z1 plus z2 squared, is equal to that complex number times its conjugate. So let's go ahead and write that out. So this expression is equal to z1 plus z2 times the conjugate of z1 plus z2. Great. Now by property A, we can say that the conjugate of z1 plus z2 is equal to the conjugate of z1 plus the conjugate of z2. So we can rewrite this as z1 plus z2 times the conjugate of z1 plus the conjugate of z2. Now let's go ahead and FOIL this out. So this expression equals z1 times the conjugate of z1 plus z1 times the conjugate of z2 plus z2 times the conjugate of z1 plus z2 times the conjugate of z2. Now I want you to notice that over here we have a complex number times its conjugate, and we have the same thing over here on the right hand side. So we can again use property f to say that z1 times the conjugate of z1 is equal to the modulus of z1 squared, and we can apply the same logic to z2 times the conjugate of z2. So we can rewrite this expression as the modulus of z1 squared plus z1 conjugate of z2 plus z2 conjugate of z1 plus the modulus of z2 squared. Great. Now I'm going to go ahead and do something a little bit tricky. I want to go ahead and replace this term in the expression with something else that's actually going to allow us to apply property G. And so what I'm going to do is I want to replace z2 conjugate of z1 with the conjugate of z1 z2 conjugate. Okay, so why exactly can I do this? Well, in order to show that you can do this, I'll just prove that they're equal. So according to property B, the conjugate of a product is the product of the conjugates. So I can go ahead and split this expression up into the conjugate of z2 times the conjugate of z1. And notice that I flipped the order of them around, and I can do that because multiplication in the complex numbers is commutative. Now, by property D, the conjugate of z2 is equal to z2. So this is simply equal to z2 times z1 conjugate, which is precisely the left-hand side. Therefore, I can go ahead and replace it with the conjugate of z1 times z2 conjugate. Great. So let's go ahead and erase this and replace it with that. So here we're going to have the conjugate of z1 z2 conjugate. Great. Now we can go ahead and apply property G, which says that the real part of a complex number, in this case, z1 z2 conjugate, is equal to 1/2 times z1 z2 conjugate plus its conjugate, which is the conjugate of z1 z2 conjugate. Great. So notice that we actually have this sum right here in our expression. However, we don't have the 1/2. So what we're going to have to do when we replace this is multiply this real part by 2. Great. Let's go ahead and write this out. So now we know that this expression is equal to the modulus of z1 squared plus 2 times the real part of z1 z2 conjugate plus the modulus of z2 squared. Great. Now let's go ahead and introduce our inequality. So we're going to say that this expression is less than or equal to the modulus of z1 squared plus 2 times the modulus of z1 z2 conjugate plus the modulus of z2 squared. And so the reason we can do this is because 2 times the modulus of z1 z2 conjugate must always be greater than or equal to 2 times the real part of z1 z2 conjugate. So that's why this inequality holds. Great. Next, let's go ahead and break up this modulus, since the modulus of a product is the product of the moduluses. So writing this out, we have that this expression is equal to the modulus of z1 squared plus 2 times the modulus of z1 times the modulus of z2 conjugate plus the modulus of z2 squared. Great. Now according to property E, we know that the modulus of the conjugate is simply equal to the modulus of the original number. So we can go ahead and replace the modulus of the conjugate of z2 with the modulus of z2. So this expression is equal to the modulus of z1 squared plus 2 times the modulus of z1 times the modulus of z2 plus the modulus of z2 squared. Now let's go ahead and factor this out. So if we factor this out, we get the modulus of z1 plus the modulus of z2 squared. And you can go ahead and confirm that foiling this out gives you this expression. Great. Now all we have to do is take the square root of both sides. So this implies that the square root of the modulus of z1 plus z2 squared is less than or equal to the square root of the modulus of z1 plus the modulus of z2 squared. So the square roots cancel out the squares, and we simply get that the modulus of z1 plus z2 is less than or equal to the modulus of z1 plus the modulus of z2, which is precisely the triangle inequality. So we have finished our proof. Okay, so it turns out that there's actually more than just one triangle inequality. We also have the reverse triangle inequality, as well as the triangle inequality for sums. And so let's go ahead and rewrite the triangle inequality so we can compare the other two to it. And I'm actually going to write it a little bit differently. However, it's equivalent to the one that we just wrote down. It's just a little bit more generalized. So we're going to say that the triangle inequality says that the modulus of positive or negative z1 plus or minus z2 must be less than or equal to the modulus of z1 plus the modulus of z2. And the reason why we can change the signs of z1 or z2 is because the modulus of a complex number z is equivalent to the modulus of negative z for all complex numbers z. So changing the sign of z1 or z2 within the modulus doesn't change the inequality. Great. Now let's talk about the reverse triangle inequality. And this inequality actually provides a lower bound for this modulus term. So the reverse triangle inequality is the modulus of positive or negative z1 plus or minus z2 must be greater than or equal to the modulus of z1 minus the modulus of z2. Great. So that's the reverse triangle inequality. Now let's talk about the triangle inequality for sums. And this is essentially just the same thing as the triangle inequality, except it addresses the case where you have an arbitrary number of z's within the modulus. So the triangle inequality for sums says that the modulus of the sum running from k equals 1 to n of z sub k must be less than or equal to the sum running from k equals 1 to n of the modulus of z sub k. Awesome. So those were some properties of the complex conjugate and the triangle inequalities. Thanks.